Hello. So this video is about module 4 of your DSP, which is IIR filter design. Okay. So what are we going to learn here? So we have IIR response filter format, the bilinear transformation method, analog filters using low pass prototype transformation. So see, we are learning analog filter design also here. Then we will be applying this transformation to get a digital filter. Okay. Then there is normalized Butterworth function. So in the textbook, you will find two types of filters, Butterworth filters and Chebyshev filters. So as per your syllabus, we will stick to only Butterworth filters. Then there is this important phenomena of bilinear transformation, and there is a small problem called as frequency warping. So which we'll see and how it is overcome also. See, so the whole design procedure of the digital filter. Then we'll end it with digital Butterworth filter design using bilinear transformation, realization of IR filters in direct form 1 and direct form 2. I think I have done this realization of direct form IR filters in direct form 1 and direct form 2 earlier. Anyway, let us see. So in this particular video with limited time, I would like let us see how much we can continue. So textbook is not pro-kiss for this, but it is text 2 which I have shared you in your Google Classroom. Okay, so let us start. Okay. So a typical IR response, how does it look like? So here you can see the difference equation contains not only the input terms, present and previous input, but also the previous outputs and the transfer function. So how do we get the transfer function, by the way? We take the z transform, then we take the ratio y of z by x of z. You can see a peculiar transfer function with the denominator, the first value being 1. And unlike your FIR transfer function, you can see the denominator here is not 1, but there are values. So there are poles present in the transfer function. Okay. And the coefficients, all the coefficients related to the inputs go in the numerator, and the coefficient related to the YFN values, the output, the feedback, they go into denominator. Okay. So let us see an example. So here there is a interesting one given, an IR filter, a difference equation. So this is what an IR filter is all about. Okay, you end up getting a difference equation which contains some values of inputs, present and previous, and the scaling coefficient and previous values of outputs. So whenever somebody asks you to design a filter, so we are trying to derive these coefficients. Okay, 0.2, 0.4, these coefficients for whatever the desired frequency response that you want. Okay, so a difference equation has been given to you, which is a difference equation that of a filter, a mysterious filter. But we are here expected to find the transfer function, the non-zero coefficients, and the impulse response. Anyway, let's get started. So how do we get the transfer function? Apply the z transform. So y of z by x of z. What do you get? As I told you, the numerator coefficients are nothing but the x of n coefficients. X of n coefficients will go into the numerator. You can say x of n minus 1. What's the z transform? Z to the power minus 1, right? So 0.4 is 0.4. Denominator, you can see for y of n, first term has remained 1, which is nothing but that of y of n coefficient. Then for y of n minus 1, had I taken this on the right side, the sign would have changed, right? That is why this change in sign. That's what the change in sign all about. So there it is. Transfer function is easy. And as per the previous template, you can see this was B naught, this was B1, this was A1. A naught is always 1. It's understood. Then, yeah, so these are the coefficients. These are the coefficients, non-zero coefficients. The coefficient z to the power minus 2 of z to the power minus 3 in the numerator and denominator, they are all 0. Okay, that's why the term non-zero coefficient. All other coefficients are 0. Okay. So, yes, then how do we get the transfer function? Okay, how do we get the impulse response? So, What is impulse response? Inverse Z transform of the transfer function is the impulse response. But when you have this kind of term, two terms in the numerator, two terms in the denominator, what we will do? We will split it. 0.2 divided by the denominator plus 0.4 into z to the power minus 1 divided by the denominator. Now, do you remember some constant k divided by 1 minus alpha z to the power minus 1? Do you remember this thing from signals and systems? This was the z transform of alpha to the power n into u of n. Remember, remember this thing. Alpha to the power n into u of n had a z transform, some constant k divided by 1, some constant k into, so here, with some constant k, with some constant into some constant k. So point 2 is that constant, and alpha to the power n into u of n. In first case, alpha equal to 0.5. In the second case, alpha equal to again 0.5, but zero point 0.4 is different. And then you can see, what about the second term by the z to the power minus 1? Here we saw, right, x of n minus 1 had a z transform of z to the power minus 1 into x of z. So similarly here, we get u of n replaced by u of n minus 1, alpha to the power n replaced by alpha to the power n minus 1, applying of the time shift property of the z transform. Okay. So that was a simple numerical for you to just to make comfortable. Let us continue. So, what are our conclusions? It's been a long time since we studied the FIR filters. So anyway, let us see what are things to remember. So IIR filter output depends not only on the current inputs and past input, but also on the past output. So it's recursive. So numerator polynomial over denominator polynomial. Impulse response has infinite number of terms because of the denominator, and the recursive nature. Okay, that's why the name infinite impulse response. The second is the transfer function has the denominator polynomial with poles. Okay, so the poles of a designed IR filter must be inside the unit circle on the Z plane to ensure stability. Okay, okay. So we will see when we design an IR filter, we will make sure that it will have the poles inside the unit circle to ensure stability. Otherwise, an IR filter may go unstable, as I told you. SIR filter would have been stable all the time. IR can go unstable. That's why we have to take care while designing. That's the second point. Then, what do they say? Yeah, IR filter offers a much smaller filter size. This we might have seen in our MATLAB simulation. So IR filters are generally much faster because of less number of coefficients and very compact sizes. But then linear phase is not easily obtained. That's a catch. Linear phase not obtained. So that's why for live audio transmissions and all can be difficult. But otherwise for general audio applications might be usable. Okay. So these are the observations. Continue. So, what are we going to learn? There have been several methods of designing IR filters. We are learning this particular method. So, what this method is, we are trying to learn this bilinear transformation design method of designing IR filters. Just when we are studying our FR filter, there are several design methods, right? The windowing method, the frequency sampling method. Here what we'll do is we will get our digital specifications, and with some sort of transformation, we'll bother about this later. We'll get the analog specification, design an analog filter, and then apply a suitable transformation from S to the Z plane to get a digital filter. Okay, that will be the general procedure. Let us see later. But the thing is, maybe we have to study the analog filter design now. Okay, let's go ahead and do that. Okay. So how do we do an analog? How do we design an analog filter? So for the time being, let us bother about only a first order analog filter. Okay, let us bother about only first order analog filter. And in your previous syllabus, usually there would have been those derivations, and we will take chances now because the time is very less. And secondly, um, it's not mentioned in your syllabus. So that's maybe as per this particular text, we may get an advantage. So let us stick to this textbook only. Okay. So yeah, analog filters using low pass filter design. Okay. So let us take this particular first order filter. Do you believe this is a first order filter? You can see S, right? So if at all you are talking about Laplace transform for a first order differential equation, you would get a single S here. So that's a first order filter. Its frequency response is obtained by substituting S equal to J mu. So this is a frequency. Okay. This here, let us say, is frequency. Okay, 1 divided by J mu plus 1. So the magnitude of this one would be 1 divided by root of 1 plus j whole square. Okay. So for this value, whenever it is 0, what's going to happen? At 0, we will have what's going to happen? Let us try to plot this particular thing. This magnitude. Let's plot this magnitude with respect to this mu thing. Okay. So at mu equal to 0, what's going to happen? 1 divided by 1. It's going to be 1. At mu equal to 1, it's going to be 1 divided by root of 1 plus 1. So that is 1 by root 2. Okay, it goes on decreasing. See, as and when this new value increases, the entire term goes on decreasing. And at mu equal to 1, it reaches a value 1 divided by root 2. Okay, 1 divided by root 2. Then after this slowly goes on decaying. Okay, so as I was telling you, so at a particular cutoff value, at a particular cutoff value of 1. Okay, so I was giving you this 1 by root 2. Actually, it's a half power point. It's a half power point, or it's also called as, if at all you convert this into dB, you will get a minus 3 dB, which you might have seen right from your first year when you are trying to do some sort of graphs in amplifiers or maybe in your LCR circuits, right? So here is the filter. Here is the filter. Okay. So how do we design a filter? Let's once again get started. A typical low pass first order filter protocol is something like this: 1 divided by S plus 1. What is a low pass filter? Low pass filter 1, which at omega equal to, which allows all the frequencies from the DC onwards up to a certain frequency. That's a low pass filter. This is a low pass filter. And yes, at omega equal to 0, we saw mu equal to 0. We started with 1, right? And then it kept on decaying. Cool. Okay. So for this particular filter, you might have seen it the cutoff frequency. Oh, what is the cutoff frequency? Usually cutoff frequency is 1, where we get the magnitude equal to 1 by root 2, that of the maximum value. So if at all maximum gain you got is 1, then 1 by root. Maximum gain you got was 10, then this would have been 10 into 1 divided by 10 into 1 divided by root 2. So that would have been something like how much? 7, something like that. Okay, so this is the cutoff frequency. What if I want a filter with a cutoff frequency of 300 instead of 1? Why would I want 1, right? I may want 300, I may want 500, I may want 1000. So worry not. So what I have to do is, in that place, we may have to replace simply S by omega C. That's it. If at all I replace S by omega C, which can be 100 or 300, I get my filter of my choice. But remember, order is 1. Order is 1. So here you can see the filter, the cutoff frequency from 1 to whichever omega C. To do that, what you have to do, you have to replace your S by omega C. Okay. So that was a simple low pass first order filter. It was a low pass first order filter. Okay. What else? What else? So yeah, uh, then what about the thing? Yeah, it's of j omega, the frequency response. You need frequency response. You replace S by j omega, then you are ready to substitute. You are ready to plot the frequency response. You just go on changing the frequency. So your x-axis will be the omega. At omega equal to 0, what are you going to get? You are going to get 1. Then after slowly you think you get whatever the kind of shape you want. Magnitude responses. This in IIR filter, seriously, we are not interested in the phase response. We are interested in only the magnitude response. So which are the critical points? At omega equal to 0, you get a magnitude of 1. At omega equal to omega c, you get a magnitude of 1 by root 2. Okay, at omega equal to omega c. Okay, if omega c equal to 300, at 300 hertz exactly, you will get a magnitude of 1 by root 2. At omega, if at all omega is equal to 1k, then exactly at 1k of omega, you get the magnitude of 1 by root 2. Okay, then afterwards, as and when omega tends to infinity, as and when omega tends to infinity, our response tends to 0. It decays. Okay. Got it. Okay, let us see. What if I want a high pass filter? Well, so what did I say? Here we had the template. Here we had the template. Right? Here we had the template. HPFS equal to 1 divided by S plus 1. If at all I replace S by omega C, I got my, so this was a filter with a cutoff frequency of 1 as I shown. If at all I wanted cutoff frequency of 100, then what I have to do? I have to replace S by 100. Are you getting this? How are you getting circuit from this? As I was telling you, if at all you have a differential equation, you can get this Laplace transfer function. So if at all you can design a Laplace transfer function, you can always go to the differential equation, right? And that differential equation describes your circuit. That's your filter. Okay. Yes. So if at all I replace S by omega c, I get a low pass filter with a cutoff frequency of omega c. Whereas if at all I replace S by omega c by S, okay, c S by omega c by S, then I will get a high pass filter. Then I will get a high pass filter. Okay, yeah, that's what we are talking about. See, you don't always want a low pass filter. See here, if at all you want replace S by omega c, you get a low pass filter or not a prototype filter, but frequency of your choice. If at all you replace S by omega c by S, then you will get a high pass filter for a change. Okay. Similarly, what else? Yeah, there are band pass and band reject filters. You want a band pass filter, you need to calculate few parameters. What are things you need to calculate? There's something called this particular frequency, which is factor of the lower cutoff frequency and upper cutoff frequency. And then what is this particular thing? This is the bandwidth. Okay. So the bigger number minus smaller number, bigger number minus smaller, that is the bandwidth. And you just have to substitute your S by S square plus omega naught divided by S into omega. Do you see here the S has been replaced by S square? Why that happened? Because a band pass filter is a combination of one low pass filter cascaded with one high pass filter. That's why uh, you need double the order. You need anyway. That's the design. You simply substitute. Okay. Then what about a band reject filter? Similar formula, but S has now gone into a denominator, just like how it works in high pass filter. Okay, so what are things that we studied till now? So analog filters. So now at this particular moment, we know how to design a first order low pass filter, prototype filter, low pass filter of our choice, and then high pass, band reject filters of our choice. But first order, okay, but first order, okay. Yes. So these are the frequencies that the transformation formula, analog to analog transformation formula. Low pass, low pass, low pass to high pass. Why low pass to low pass? Because low pass from prototype filter of cutoff frequency 1 to frequency of our choice. Okay. So here you can see a simple example has been given. Low pass filter prototype has been given. Now we want a high pass filter with a cutoff frequency of 40. What do? We simply replace S by 40 by S and substitute in the formula 40 divided by S. And there we get our high pass filter. Okay. Then if at all I want a band pass filter, see band pass filter with a center frequency of 100 per second radians per second and a bandwidth of 20. Okay. Center frequency of 100 automatically he has given. Okay. So now we need not do this omega L into omega U. He gave 100. So we use 100 bandwidth. Had he given lower cutoff frequency of 20 and upper cutoff frequency of 200, then maybe we would have taken root of 20 into 200. Okay, 20 into 200 we would have done. Here nothing like that. He gave single frequency. Okay, in the mid of the band. Okay. So that's what. Hmm? Then yeah. Now the thing is okay. Low pass filter taken care. About designing higher order analog filters, we will come to that. Okay, higher order analog filters will come to that. There are some simple formulae. Okay, whose derivation are out of the scope. So we will come to that. For the timing, let us see. Okay, this was the first step, right? Designing an analog filter. Now somehow we have to migrate from the H of S to H of Z. Okay, we have to migrate from H of S to H of Z. How are we going to do this? So that will do. There have been several techniques, but the tested and the best technique is bilinear transformation. So what we'll do, bilinear transformation has a small glitch. So we'll derive the bilinear transformation, understand what is the problem, and then we will address it. How do we tackle it? It's a very important derivation also, okay, which usually pops up in exam. Okay, so that's why we'll be we are interested. Okay, let us see, let us try and understand and derive the bilinear transformation method, the bilinear transformation method of IIR filter design. Okay, what is the method actually? Let us see, let us see. So we will start with this particular figure. Okay, if at all I happen to have a curve, say I happen to have a curve, and I want to know I want to know the area under the curve from 0 to say some duration t. How do I do it? I integrate, right? That's the use of integration, right? Integration allows us to find area under a curve. So if at all I integrate from 0 to t, some wave x of t, I get the area under the curve, right? Cool. Okay, everything is cool. So 0 to t x of t dt. So that is integration. And how do you do integration, by the way? If let us take the Laplace transform, y of t becomes y of s, x of t becomes x of s. Integration is 1 by s. Remember, differentiation is s, multiplication by s. Integration is 1 by s. Okay. And there is just like we have h of z, just like we have what is h of z, by the way, the transfer function, it was y of z by x of z. Similarly, for Laplace, let us have a transfer function, Laplace transform g of s, which is y of s by x of s, and that would be, see here, y of s by x of s. That leaves us with 1 by s. Okay. So first step in our derivation is for area under the curve, for an area under the curve from a duration 0 to t. Okay, so it was decided that it's simple integration from 0 to t. Laplace has been applied, and we got this thing 1 by s. Let us continue. Let us continue, and let us try to get its digital counterpart. Okay. Now, what changes have been made here? Now, its corresponding digital counterpart is this particular thing. So, what has been done here? Wait, let me continue. Let me continue here. Yeah, yeah. Okay. So, now let us talk about applying the same thing in the digital domain. Let us try to apply the same thing in the digital domain. Okay. So, considering this to be uh, discrete one. Okay. So that means for continuous time, we x of t was fine. We got y of t, which is the area under the curve. Now let us try to do this piecewise. Let us try to break it into smaller pieces. So say we have come to this particular piece here. So value found till now, say here is y of n minus 1. Okay, that's the area found till this particular instant, and there is this amount of area yet to be calculated, this amount of area yet to be calculated. So y of n is going to be the area up to y of n this particular instant. Okay, say you have calculated area up to y of n minus 1, and you want to calculate area up to y of n. So what would that be? So that would be y of n minus 1, the area till y of n minus 1, till n minus 1. Okay, this instant plus this particular area under this particular box. Okay. How do you think? Now let us see this particular box. Let me simplify this for you. See, here is a box. Here is a box. Not exactly a well-behaved rectangular box. Okay. So what do you think? How do you calculate the area of this particular thing? How do you calculate the area of this particular? Say the value at this particular instant is say x of n minus 1, it seems. Let us say it's an amplitude. Okay. Amplitude of this larger edge is x of n minus 1 and smaller edge is x of n. Let us say, okay. Width of this is the duration t. Width of the box is duration t. So what is the formula of a rectangle? Length into breadth, right? Now see, one side is having a height of n minus 1, x of n minus 1. Another side is having a height of x of n. So can I approximate this to be, both of them to be equal to x of n minus 1 plus x of n divided by 2? Now suppose, see, there are two poles here, okay. Say the height of this pole is 11 feet. Height of this pole is say 9 feet. Then, if at all I want to find the area in this particular area, can I take it as 11 plus 9 divided by 2? That would be 10. So this can be approximated by, not always true, but can be approximated to be height of 10 and width of some t, right? Cool. So that's what we are going to do here. So what we'll do, we will resort to this particular approximation where the value, the area under the curve at y of n, we will take it as area till y of n minus 1, which is up to n minus 1 into t. And for this particular curve, what we'll do, the area will calculate it as the amplitude x of n and the amplitude x of n minus 1 divided by 2, right? 11 plus 9 divided by 2, 10 into the width, which is the sampling period. Okay. See, that's the substitution we have made. You know what we did just now? This particular earlier approximation was y of t, which was continuous. Okay. Earlier value. Now this is an approximation. This is a approximation, and the approximation means it's in digital. So we have migrated from a differential equation, that integration thing, into a difference equation now. Okay. Difference equation. Okay. And then we will apply the z transform, y of z, z to the power minus into y of z, t by 2 into x of z plus z to the power minus into the x of z. Now we take the ratio g of z. Remember, earlier we took a ratio g of s. We called it as the Laplace transfer function. Now this is h of z. This is the what is it? Z transfer function. Z transfer function. Okay. Now what was our task? We wanted to migrate from an analog filter to a digital filter. That means we want to migrate from analog transfer function to digital transfer function. The Laplace transfer function to Z transfer function. So what was that thing earlier? 1 by s. Now let us equate that 1 by s to this particular thing, which is t divided by 2 into z plus 1 divided by z minus 1. So there we have it. So the mapping from s to z is this here. Okay. So this is the simple derivation of the bilinear transformation. S equal to 2 by t into z to the z minus 1 divided by z plus 1. So what is the method now? The method is simple. To design an analog filter, you simply replace the s by 2 by t into z minus 1 divided by z plus 1. You get a filter with z terms. Cool. But now the problem is the analog filter was stable, but the corresponding digital filter, will it be also stable? Let us see. Let us analyze the, let us do the stability analysis of this particular mapping function. Okay. As I said, the derivation of the bilinear transformation is important. The mapping from S plane to Z plane, the stability analysis and the frequency mapping is also equally important examination question. So let us be just curious. So which is the thing that we are trying to map? Um, this thing. Okay, we are trying to do the stability analysis of this particular mapping function. Let us uh, study. Okay, so instead of having it in terms of this s, we have had it in terms of z here. So let us see. So if at all, what is meant by a stable thing in the Laplace? So the stable thing in Laplace is, this is the boundary of stability, right? Anything on the right side of this j omega axis is unstable. Anything on anything on the left side of the j omega axis is stable. So what we should get, the left half of S plane should be mapped onto inside the unit circle in the Z plane. Is it happening here? Is it happening here? Let us see. Yes. So here, as you can see, what we'll do, we'll make a small change. In the expression, let us substitute with Z equal to R e to the power j omega, the digital frequency, and S equal to sigma plus j omega, the analog frequency. See here, omega d is the digital frequency, omega a is the analog frequency. So the relationship S equal to 2 by t into z to the power minus 1 divided by z minus 1 divided by z plus 1 becomes something like this. So then this will be converted into sigma plus j omega into this particular equation. And you can see here, by only keeping the real parts. Now, where did we get this particular equation? It is covered in the next page itself. Okay. So now see here, for this particular equation, let me equate only the real parts, the sigma. Okay. So sigma will get this particular equation. Observe the equation very clearly. Okay. Observe the equation very clearly. So what we want is, whenever we map this thing from analog filter to a digital filter, we want to transform a stable analog filter onto a stable digital filter. So what is a stable analog filter? The one which is having all the poles on the left side, or the entire j omega axis, if at all this maps onto the unit circle. Because what's the deal with unit circle? Unit circle is the boundary of stability in the z plane, or for digital filters. So let us see this particular region. So this particular radius r equal to 1. Okay, unit radius, that's what indicates. So in this particular equation, for r value less than 1, what's going to happen? For r value of less than 1, say r equal to 0.5, then what's going to happen? You end up getting sigma value negative. Okay, that means all the values of r inside the unit circle will map onto the left half of the S plane. Okay, that's cool. For r value greater than 1, say r equal to 2, 2 square minus 1, yeah, bigger number, positive number, sigma will be greater than 1. So for any pole or any number lying outside the unit circle, its corresponding S plane will be outside the, on the right side of the S plane. For r equal to 1, sigma equal to 0. So this particular value, sigma equal to 0, indicates the boundary and maps onto the unit circle. So the conclusion of the story, the stable analog filter is getting mapped onto the stable digital filter. So stability wise, the filter is doing good. The bilinear transformation seems to work, but we have concerns in the frequency mapping. Let us see what it is. Okay, the frequency mapping has a small issue. For this, what we'll do, let us keep the sigma out of it now, because the stability has been taken here. That's why what we'll do, this particular thing, let us only take s equal to j omega a, assuming that it is on the, for sigma equal to 0 plane only, and let us only study the uh, um, what frequency behavior. Okay, so or this could have been done by, in this particular previous expression we had two terms, right? One for sigma and one for omega, the real omega and the imaginary one. So we could as well analyze this particular segment. It still gives us the same results. Okay, so let s equal to j omega a and z equal to e to the power j omega d into t. Why I'm telling this is because this is compatible with your prescribed textbook. Okay. So you see here, with this particular mapping, okay, So let me substitute s equal to in this particular thing s equal to j into omega a, z equal to e to the power j omega d into t. Okay, minus 1. Then this is the transformation. What is this component to divide into something? I used to do it in basic electrical science, if I remember. Okay, we have done that particular thing to get this particular mapping, and this mapping j getting cancelled, 2 getting cancelled, and the substitution, we have a mapping now. At the end of this entire derivation, we have a mapping. What's the mapping? Every analog frequency omega maps to the digital frequency with the tan function. Okay, so analog frequency omega a is equal to digital frequency related by this equation 2 divided by t tan into omega a divided by 2, tan of omega a by 2. Now what's the deal with the tan? Do we remember tan? Tan is a spooky function. Okay, so what is that? From 0 degree, 0 degree, 30 degree, 45 degree, 60 degree and 90 degree, as highlighted by all of us, I think, in the first PUC. Let me tell you the numbers. Okay, 0, 1 by root 3, then 1, then root 3, then 1090, it's infinity. What is particular thing? Tan is a weird function. So the mapping, something looks like this. It goes to infinity. So what's going to happen? Lower analog frequencies will map to some lower digital frequencies, fine. But for analog frequencies, as and when analog frequencies increase, their mapping is going to be suddenly like, something like this. It suddenly increases, zoom. Okay, we have a problem. We have a problem here. The mapping is not cool. Okay. So this particular non-linear mapping is called as warping effect. Remember the term. It's called as warping effect, and it should be eliminated. It should be eliminated. Let us see how big is this particular problem, or how crucial is this particular problem. See here, author has given this particular thing, a mapping from analog frequency to the digital frequency. The author has given us this analog frequency digital frequency problem. If at all we take a normal filter and we'll directly transform it to digital filter, then what's going to happen? Say digital to analog transformation, if at all we perform. So what did I tell you? The normal tan function is this particular curve, an exponential curve. So a tan inverse function is going to be a saturation curve. It's going to be a saturation curve. So that's why you can see a digital frequency, whenever an analog frequency, right? What is the method by the way? What's the method Bilinear transformation? What does it suggest? You design an analog filter, then afterwards replace S by 2 by T, Z to the power Z minus 1 divided by Z plus 1. Here is a problem. The analog frequency to digital frequency mapping. So here is the relationship. So the mapping from analog to digital frequency is tan inverse, a saturation one. So what has happened with saturation one? See here, few values have been given. 0 is 0, cool. 0.32 turns out to be 0.25. A 1 turns out to be a 0.4, and even a maximum number of, I don't know, it's going till here. Maximum number, even maybe 100, maybe 100 times WS, okay, or maybe 300 times WS. They will also map to a maximum number of 0.5. Okay, they will also map to. So what that means? What that means is you can have some sort of low pass filters. You can have some sort of low pass filters here. Yes, they will map onto corresponding low pass filters here. Like okay, wait. Okay, they will map onto low pass filters here. Say you have a band pass filter, something like this here. They will behave little spooky. Okay. Suppose I have a band pass filter somewhere in this particular range, then here it's going to get squeezed. It's going to get squeezed because all frequencies, suppose I have a very large band pass filter here in this particular range. Say I have a very large band pass filter in this particular range here. Say a very large band pass filter. It still maps onto. it still maps into a very small band pass filter in the digital domain. So we have a problem. So this non-linear, okay, linear is cool. If at all I am had a mapping something like this line, I don't mind the scaling factor of 1, 2, 3. I don't mind the line going like this. I don't mind the line going like this. But this particular thing, like tan wave, spoiled all the party. Okay, this is not cool. Okay, this is not cool. So what should we do? So this non-linear frequency mapping is called as frequency warping effect, and it should be eliminated. How do we do this? See here, a tan is function of the problem, right? So what we will do, the moment we take our analog frequencies for the design, first thing we'll do is let us apply tan. First we will apply a tan thing. So when you take a tan thing, tan with tan inverse, what you get? You get the value itself, right? So the entire thing is nullified. So what's the deal? Before applying the bilinear transformation, your digital frequency shall be pre-warped. So this particular thing, tan inverse was a problem. So how did you tackle it? By taking 2 by t tan of the digital frequency into t divided by 2. So this particular action that we take is called as pre-warping. It's called as pre-warping. Okay. So what's the method now? So so here author has given an example. Okay. So three frequencies chosen: 10 radians, 150 radians, and 314. 10 radians at lower frequency came up to in the digital domain as 9.99, almost there. Analog frequency and corresponding digital was there and there. When 157 radians were chosen, a bigger number, 157 were converted to 133. Worrisome, right? It's not the exact frequency. And when 314 was taken into consideration, it was converted into 252. This is what we are talking about. Warping effect, not cool. And yes, we can tackle it. Take time. Okay, that's it. Okay, take. So what is a typical bilinear transformation method? So whenever you will be given the digital frequency for the design, first thing you do is go for pre-warping by applying this particular formula. Okay, applying this particular formula. Then what else? Yes, in case of band pass filter, there will be two cutoff frequencies, right? Take take their values. Take pre-warping first, then afterwards you calculate the bandwidth and the center frequency. Okay, so it can go wrong sometimes in case of band pass. One should be careful. Okay, this is the first step. What is the next step? The second step is perform the normal transformation. Okay, wait a second. Let me. Yes. So next step is perform the transformation as usual. Perform the transformation as usual. Whether low pass, high pass, band pass, band reject. Design the filter. Go ahead. Then afterwards at the end, simply replace the S file 2 by 2 z minus 1 divided by z plus 1. There you go. So in the next video, I will be covering the numericals. Okay. In the next video, I will be covering the numericals. So there are the specific filter that we'll be talking about would be something like a Butterworth digital filter. We'll study a Butterworth analog filter, then Butterworth digital. Let us have an example of one low pass, high pass, band pass, and band reject. Okay. That's it. Bye.